Good evening, this is Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. So, today we will continue the heteroscedasticity problem. In the last lectures, we have discussed or we have started little bit about the heteroscedasticity issue. So, how it is coming to that in the econometric model and how it is very useful for discussing that particular issue. So, we highlighted that heteroscedasticity has two specific aspects. So, just I am bringing a little bit more here. So, this is heteroscedasticity. Okay. So, then this is scedasticity. So, that means briefly it is the equation of unequal error variance. Okay. So, if it is turned to equal variance, then that will lead to homoscedasticity issue. Homoscedasticity problem. Okay. So, that means we start with the fit a model first. So, the moment you have estimated model, then like so many other econometric problem like multicollinearity, autocorrelation, etc. So, we have to also check the heteroscedasticity problem. So, heteroscedasticity basic objective is to check whether the error variance are equal or unequal. If it is equal, then it is a good sign. You have to go ahead with the econometric problems and you can use that model, or you can say that this model is best fitted and can be used for forecasting or policy use. But if the error variance are not equal, then you have to redesign, reformulate, or you can say restructure till you get the estimated model which is purely homoscedasticity in nature. So, that means there should not be any heteroscedasticity. So, what is that? That means there should not be any unequal error variance. So, we start means the starting point is you must have some estimated model. Then in the meantime, you must find out the error component, then find out error variance for each and every sample point for U1, U2, U3 like this. Then if it is equal over the different time periods or different samples, then obviously, so if it is equal, then it is homoscedasticity. If not equal, then it is heteroscedasticity. Then you have to recycle it till you get the homoscedasticity. Okay, so that is how the problem is all about. So, that is how I have started. So, let us assume that the problem has heteroscedasticity. So, then your objective is to make the variance unequal variance to equal variance, and that will lead to homoscedasticity problem. So, this is the basic statement. So, now that means theoretical means by statistics, heteroscedasticity means the presence of unequal variance in the econometric models. So, unequal variance means it is related to error terms, unequal error variance in the particular econometric models. So, now if it is unequal error variance, then that is one of the negative point for econometric modeling, that will give you red signal. So, you turn into green signal, that is the homoscedasticity problem, then you have to go ahead with the forecasting issue. So, now, so the moment you have a heteroscedasticity, so now like degree of autocorrelation, degree of multicollinearity. So, similarly you can have the framework or structure, nature of this heteroscedasticity. Is it too much problematic or very small problem altogether? Okay, so then we will see how is that actually safe. So, there are various ways we can represent the heteroscedasticity problem. So, let us say case 1 here. So, what is the issue of heteroscedasticity? Heteroscedasticity means I will take x observation here. So, that means x1, x2 up to you say xn. Okay, these are the x observations. All right. So, now this side I will put residuals. Okay, residuals. So, that is means error terms. Okay, error variance. Okay. So, now this I will plot like this. Okay, I will plot like this. These are all items, error items. Okay. So, now these error items are in a it is more or less equal spread, very close to each other. Okay, you see the gap is very close to each other. So, that means if this is the case, then we can call it is not heteroscedasticity problem, rather it is a homoscedasticity problem. Okay, so this is the variance issue only. So if the variance is large, then it will affect the models. If the variance is low, it will be less effect on the model. So we try to build a structure where there is a less error variance. So that is how that is the objective of this particular process. Okay, I will take a case 2, another case. Okay, so another case like this. The same structures, I will put it here x, and this side is residuals error terms. Then obviously I will take like this. Okay, the plot will be like this. Okay, the plot will be like this. So this is means it is the if the error variance will be errors are coming like this way, then there is a heteroscedasticity problem. This is heteroscedasticity problem, and that is too it is the increasing sample of error variance. This is the increasing sample of error variance. Okay, increase sample of error variance. Okay, I will take another case. I will take another case here, case 3. Okay, I will take similar like this way. Then this side x, this side residuals u. Then the problem will be like this. Okay, so this is also heteroscedasticity problem. The nature is the heteroscedasticity problem, and here it is a decreasing issue, decreasing nature of error variance. Okay, so now we will take case 4, another case. So there may be like this, it may be like this, it may be like this. Okay, then it will be like this, then it will be like this. Okay, so this is also heteroscedasticity issue, with both decreasing and increasing nature of error variance. Okay, so there are altogether there are 4 different shapes of heteroscedasticity problems. Case 1 where there is no such heteroscedasticity at the minor level, so it is not a problem for econometric modeling. That model can be considered as the best models and can be used for forecasting or policy use. But in the second, third, fourth cases, sometimes error variance is increasing, sometimes error variance is increasing, and sometimes both can be go simultaneously. In that case, it is a problem for econometric, you need to remove it. Okay, so exactly how is the step? If you will take another type of structures, you see here, this side I will take 3-dimensional picture. If I will plot, then obviously the picture will be coming like this: 0x, this side y, and this side u. Okay, or we can say y head. All right, so like this, the you plot all these things like this. This way you will get like this way. So this type of sequence is called as a, it's looking like homoscedasticity. Okay, so this type of structure is called as a homoscedasticity issue. But you see, I will take another case here. Okay, another 3-dimensional pictures. Okay, so this is a x, this is a o, y, this is y head. Okay, so then I will draw like this. Okay, okay, this is purely heteroscedasticity problem. Okay, so now now we come to know that the basic definition of heteroscedasticity is that unequal error variance. Sometimes the error variance are in a increasing trend, sometimes error variance are in a decreasing trend, sometimes error variance are very constant with respect to whatever shape of the sample, and sometimes there may be increasing, decreasing, and constant. It can go together. So that depends upon what is your sample observations. Okay, if the sample observation is exclusively very high, then you will find there is everything is there, increasing, decreasing, and constant. So anyway, if that is the case, so we have to bring the sequence or structures where there is a error variance are homogeneous in nature. So that should be our aim, and that should be our requirement for econometric modeling. So now once you know the nature of the heteroscedasticity, next obvious question is what are the causes behind this heteroscedasticity? Why heteroscedasticity seems to be there in the econometric model? There are various reasons for that. Okay, so causes behind this heteroscedasticity problem. First is there is a concept called as a error learning models. Error learning models. Okay, you know, I have mentioned in the last class the quotation like success is the pillar of failure is the pillar of success. So that means if you fail, then obviously it will give you learning lessons, and that lessons or learning will be very useful for futures. Okay, so error learning model also behaves like that way. So means it will give you a equation like this way. This is error, and this is how it's called as a learning ability, or you can say experience. Okay, or you can say committing mistakes with respect to sample of different time periods. So over the time periods, when we will do things after time interval, different time interval, then obviously you will find your error variance will start decreasing. So it cannot be uniform or it cannot be constant. Okay, so today you have no experience, that's why you are doing and you are committing lots of mistakes. So tomorrow you have little bit experience, then obviously you do commit errors, but the amount of error will be less than to first case. Again, next stage, you have experience, you gain lessons, or you gain message, knowledge, etc. And obviously error will be committing less and less. So that is how error cannot be constant over and over time. So it will be in a declining trend. As a result, it will lead to heteroscedasticity issue. Okay, so this is first causes behind this, and this is very interesting, very important one. Okay, then growth and trend factors. Okay, you see, if we in the econometric model itself is going to discuss the interdependence between dependent variable and independent variables. So when we approach a particular problem, societal problems, then we are tackling various variables to a particular issue. So variables behaviors are very much not constant. It will be behave with respect to different condition, different situation, different places, different time framework. So that's why over the times the variables behavior is somewhat increasing, decreasing, etc. So this is how it cannot be constant. As a result, so all the variables are behaving in a different ways. So it will give you signal that it cannot, and that means it will give the indication that error variance cannot be constant. It will be unequal by default. Okay. So then third point is that this is called as a growth and trend factors. Growth and trend factors. Then natural tendency. It's a natural tendency of the variables. Okay. For instance, some of the cases variable itself by nature it will be in a increasing or decreasing trend. Take a case of earnings. Okay, earnings is a variable. So I will take few different industry, the software industry, then corporate financial world, then I will take some agricultural sector, then I will just compare the earnings of agricultural peoples and earnings of industrial people and earnings of say finance people, say banking industry. Then if you compare, then obviously by default the earnings of three such industry are completely different. And if I will club all these variables together, then I will ask what is the impact of earnings on say savings. Then obviously you will find there is a heterogeneous problem, means a heteroscedasticity problem, because the sample itself give you the problem setup. It will give you indication that there is you can say heteroscedasticity problem, because the variable itself behave in a different way. In fact, there is also measurement errors. Like measurement error means sometimes you are asking some question to respondents. So some respondents are behaving very accurately and they are very unbiased, but some of the respondents are behaving some other way around. It's a bias. So if you club these two respondents, then obviously it will lead to heteroscedasticity problem. So by default by techniques you will find some heteroscedasticity. It is not artificial instrument. It is by this principle or structure it will come automatically. Okay, so this is how the the measurement error also have a problem of a heteroscedasticity issue. Okay, so this is measurement errors. Then fifth, data improvement technique. Okay, data improvement technique. So this is another important variable. So generally over and above, if you will apply different techniques with respect to a particular problem, then by technique itself it will be minimize the error. For instance, if you will apply OLS, GLS, WS and maximum likelihood estimator of a particular problem, then obviously you will find the error cannot be constant in by each and every technique. So, by technique itself it will generate lots of you can say errors, or you can say it will give you heteroscedasticity issue. So, obviously even if the technique will also minimize the heteroscedasticity issue. For instance, if you are applying if you have a problem and if you are applying OLS, then there may be heteroscedasticity problem, but if you in the same problem if you apply WLS or GLS, then heteroscedasticity problem can be solved. So, that is how technique itself can create a heteroscedasticity problem, it can also solve the heteroscedasticity problem. So, different techniques also have a cause for heteroscedasticity problem. Okay. Then sixth, outliers. Okay. Outliers is a problem of heteroscedasticity. You see, outliers means it is a data point which is highly distant from other data points. Okay, highly distant from data points. That means it is going against the homogeneous clusters. So, suppose there are 10 items here and 2 items in the few other places. It is very highly distant from other data points. So, then in that case it will be heteroscedasticity problem. So, you have to be very careful about how you have to remove this. In fact, in that case you can either you transfer this data, or you can say go for the structural break testing etc. to normalize the situation. Otherwise, if you go by simple modeling by integrating all these samples at a time, then obviously you can say heteroscedasticity will be coming into the picture, and you need to have a solution for that. Okay. So, this is outliers problem. Then similarly, omission of relevant variables. Okay, relevant variables also another items which can solve the which can add the heteroscedasticity problems. For instance, last class I have discussed the issue like stock price with industrial index of industrial productions, then money supply, then wholesale price index, exchange rate, etc. So, in that case I have mentioned very clearly, if you will drop a particular variable, important variable, say money supply, or you can say wholesale price index, then obviously it will give you a message that either it is a autocorrelation problem, or it may be a heteroscedasticity problem, or it may be both also. So, that is why inclusion of a relevant variable means exclusion of a relevant variable also very problem. Similarly, inclusion of unnecessary variable also problem for this heteroscedasticity and autocorrelation. So, you must be very careful what are the relevant variables you are putting in the system and what are the unnecessary variables you are putting in the systems. Okay. So, necessary variables should be included and unnecessary variables should be excluded. If it is other way around, then obviously it will be problem for heteroscedasticity. Okay. So, this is how omission of relevant variable or inclusion your exclusion of this is omission of relevant variables or inclusion of unnecessary variables. So, that is how it is called as a inclusion of unnecessary variables. Okay, this is another point you can consider here. So, then skewness of the distributions. Okay, for instance, if we will take a very group of peoples in a particular setup, let us say take a case of income. So, there is a income distribution. Income itself is a inequality in nature. Okay. So, as a result, it will affect the heteroscedasticity problem. Some of the variables by default by nature they are unequal variance. So, it cannot be have. Some of the variables have a very equal in nature. For instance, take a case of very well developed financial market or capital market, and you observe the stock price, or you can say observe the exchange rate, etc. Then you will find it is a very less volatility. Okay. So, then if the market is very stable, then you will find error variance will be very less. If the market is unstable, then you will find huge error variance. In fact, if is very volatility, that is called as a volatility modeling. If volatility is very high, then obviously the risks will be coming into the picture, and in fact it is very interesting for different players, but it may be affecting the economic system. So, but it cannot be equal, variance should not be exactly equal for each or for different problem setup or different condition. For financial market or you can say capital market case, so error variance should not be equal perfectly, but our objective should to make a stable market. But if there is a stable market, then obviously people cannot have the risks, or people cannot go for investment, etc. So there is need of something, but it should not be extremely high, it should be very optimum one. Okay, so this is how the structure of skewness of the distribution. So that means it is a skewness issue. Okay, so similarly there is another concept called as a data transformations. So in fact heterogeneous when there is heterogeneity, then obviously, or heteroscedasticity, then obviously one of the standard trick is to go for transformation. If you go for transformation, then obviously it may turn to homoscedasticity problem. But the thing is, the transformation should be very accurate, very perfect, very feasible one. If the transformation rule is or the transformation technique is not unbiased, if it is totally biased, then obviously it will add heteroscedasticity problem rather than it will reduce the heteroscedasticity problem. Okay, so the transformation technique should be perfectly okay for this particular problem. Okay, so that means in 10th there is a transformation technique. Okay, similarly another point is very beginning itself, wrong functional form. So that is also another factors which add the autocorrelation problem also. But transformation means if you go for wrong functional form, say linear model to non-linear, or non-linear model to model, and if you go for solving the particular theme, then obviously it will add heteroscedasticity problem. So you must be very careful about that one. So that means this is called as a wrong functional form of the model. So like this there are several you can say several ways you have to find out heteroscedasticity can be coming into the picture. So the cause is not a single one, so there are multiple causes. These are the means these whatever factors we have discussed, these are the relevant causes through which heteroscedasticity is always be there in the econometric problem. Always means in most of the cases, not every case it cannot be, but most of the cases you will find heteroscedasticity is a issue. Okay, so now you get to know what is heteroscedasticity problem, what are its nature, and what are causes. Then finally we like to know what is the consequences. Okay, so then we like to know consequences. Obviously, so far the consequences is concerned, we like to highlight the blue property. Okay, so suppose the consequence is a factor, then we have to see the blue factors. Okay, best linear unbiased estimators. Okay, best linear unbiased estimators. So that means it should be linear, it should be unbiased, minimum variance, then consistent, and finally not least it's a efficient. Okay, very parameters should be very efficient. Okay, so now suppose heteroscedasticity is there, it does not affect the unbiasedness properties. Okay, it will go with the unbiased property, but it is not efficient. Okay, so it will affect it is not affect this one, so it will affect this one, this will affect this one, this will affect this one. So that means when heteroscedasticity is present in the model, then estimated parameters will not follow the minimum variance, will not follow consistent property, it will not follow the efficient property. So that means because the variance is very high and it is totally unequal. So if the variance is low and equal for every sample points or for different sample points, then obviously so this will lead to, you can say, blue property. So our aim is to transfer this particular inefficient, or you can say inconsistent or larger variance to minimum variance, or consistent, or you can say efficient. That is the consequence part of the model. So if it is not going to maintain the minimum variance property, consistent property and efficient property. So as a result, this model cannot be considered as the best, and it cannot be used, or it should not be used for forecasting and policy. You need to have a solution for that. That means again you have to redesign, reformulate, restructure till you get the model where all the estimated parameters having minimum variance, unbiased, consistent and efficient. Okay, this is how the consequence part of this heteroscedasticity problem. Okay. Next is the detection criteria. Okay, so like multicollinearity and autocorrelation, heteroscedasticity can be detected by various methods. So there are large number of methods available to detect the heteroscedasticity problem. Accordingly, you have to find out its also solution for that. Okay, so what is that particular solutions? You see here, means forget about first solution. Let's first we detect, then we will go for its solution. So detection criteria, there are several methods. I will just highlight a few methods here because of time constraint, and mostly these three techniques are usually applied to detect the you can say heteroscedasticity problem. It is very difficult to go the way we have discussed till now, but we will find out some simple way how to detect the heteroscedasticity problem. So that simple way we have to structure here. So one method is called as a Spearman rank correlation method. Okay, so that formula is R E upon X equal to 1 minus 6 summation D square divided by N into N square minus 1. Okay, so okay, what is E and what is R E X? That means E is another one variable, X is another variable. We start with Y X, then Y head and E, but in the Spearman rank correlation, to detect the heteroscedasticity, we like to integrate X and Y. Okay, so we like to know what is the correlation associated between X and E. If there is such correlations, in fact it looks like multicollinearity type situation. So if it is if that particular correlation is statistically significant, then it will have the heteroscedasticity issue. So that has to be removed. So 1 minus 6 summation D square into divided by N into N square minus 1. So D is the difference between E and X. Okay, so we have series of points like E1, E2, E3 like this, then X1, X2, X3 like this. So we have to find out the difference. The difference is called as D1, D2, D3 like this. Okay, so this is how you have to make summation, find out again D1 square, D2 square, D3 squares, then you find out summation D squares. Okay, summation D square. So the moment you will get summation D square, then you put it here, N equal to total number of observations. Okay, total number of observations, and this REX represents correlation coefficient between E and X. So now we will get R value. So now you have to apply T statistics. So T is nothing but R square by 1 minus R square followed by N minus 2. Okay, so now if it is statistically significant, then there is a presence of heteroscedasticity that has to be solved. Okay, but rank correlation it's a very beautiful technique, but it has lots of different structures and different shapes. So we have to very careful about that. One of the different one of the interesting structure is that having a same rank in various cases. Okay, if there is a same ranks, then this particular formula cannot be used. So that is then if some cases the ranks are not ranks are same for different observations, then obviously we use this formula 1 minus 6 summation D squares. Okay, then 1 plus 12 into M1 minus M1 to the power 3 minus M1, that means M1 into M1 square minus 1, then plus 1 by 12, then M2 square M2 3 minus M2. So it will continue. Okay, like number of equal ranks. Okay, so divide by N into N square minus 1. Okay, N into N square minus 1. So this should be the criteria when equal ranks are there. For instance, let us say D1 D2 are equal, so that means 2 2 is there. So it is in one case 1 by 12. So it is 2 to the power 3 minus 2, like this. You have to calculate the rank correlation coefficient. Again, once you have rank correlation coefficient, then you have to again test through t statistic. If it is significant, then obviously there is heteroscedasticity problem. If not, then it is a homoscedasticity problem. So it means the moment t is significant, then obviously you have to redesign, restructure and reformulate it until you get the a homoscedasticity transformation or homoscedasticity problem. So if it is not significant, then by default the presence of heteroscedasticity is not a serious problem for the forecasting or policy use. So you can go ahead with that particular heteroscedasticity. Of course, heteroscedasticity cannot be totally 0. Sometimes it may be available at a minor level, but that is not a problem. But if it is at a major level, so then you have to remove for that. You must have some solution for that. Otherwise, it cannot be used for forecasting or policy use. All right. Okay, the thing is, when you will calculate R here, R you calculate, then you know this is correlation coefficient. R is lies between -1 plus 1. Okay, so it is, you know, it is the R square technique. So obviously, you know, that is how you need T. T can give you the better signal to significance of the a correlation coefficient. Only getting the R is not a sufficient, because it will give you the degree of association. Means obviously, like, you know, multicollinearity, it will give you the linear association between these two variables x and u. So now if the degree is high, then there is a presence of high heteroscedasticity. If the degree is low, it is a presence of low heteroscedasticity. So accordingly, you have to restructure and redesign till you get the situation where it is the means the situation where the degree of association is at the 0 level or it is close to 0. If it is at the higher level close to 1, then it is a serious problem. So you have to restructure the model. Okay. So this is one technique through which you have to solve the particular problem. Second technique is called as a Goldfeld and quadrant test. Okay. GQ test. Okay, this is another test through which you have to detect the heteroscedasticity problem. What is this test? In that case, we use F statistic. F statistic is explain sum square 2 divided by n minus c by 2. Okay, minus k. Okay, minus k divided by ESS1 n minus c by 2. Okay, minus k. Okay, minus k. So this is ESS2 and ESS1. So that means this is explain sum squares at the level 2 and explain sum square with the level 1. So what is the level 2, level 1? So that means you see here. So we have x and we have e. Okay, so e1, e2, e3 and up to you can say en. Okay, this is how the structure. But you know, when the sample size is very less, so this particular method may not be very perfect fit. For a small sample, then you go for rank correlation, you can find out the solution. You know, these techniques are there are various techniques. Various means all techniques are not similar structure, dissimilar shape. There are different structure and different shape. They are also very strong in any particular problem. This particular technique is very useful for large number of samples. Okay, so what is that structure here? So the moment you will get this type of error structures, let's say it has a 500 errors. Okay, so for 500 observation points. So what you have to do? So you first arrange in ascending to descending orders. Then you remove some middle points. So that middle point removal is called as a C, common points. Okay. So now say 500, you drop 50 in the middles. Then you if you drop 50, then it will reduce to 450. Then you know 1 to first you divide the entire structure into 2 equal parts. Then accordingly you club like this. Okay. So you remove this particular point. Then this you will find out ESS1 and you will find out here ESS2. Okay, so this is C, the omitter of variables. Then accordingly you find out the F statistic. If the F statistic is statistically significant, then there is a heteroscedasticity problem. So if the F statistic is not significant, then that will be created, you can say that will give an indication that it is a homoscedasticity problem. So if it is a homoscedasticity, then there is no issue. You have to go ahead. If it is F is found statistically significant, then you have to redesign, restructure till you get the a homoscedasticity issue, means transformation of homoscedasticity. Okay. So similarly, there is another test called as a white test. Through through which you can check the detect the heteroscedasticity. In the white test, so we need to integrate with the y head and e. Okay, so first you get y head and then you find out to e. So that means followed by y and x information. So you process it to get y head. Okay, so by process you will get y head, then you have to obtain the e, then you have to build a model here like this. Let's say the sample point, there are 3 variables in the system, so you take like this, gamma 1, gamma 0 plus gamma 1 x1 plus gamma 2 x2 plus gamma 3 x3, okay, plus u. Okay, so estimated model will be gamma 0 head plus gamma 1 head x1 plus gamma 2 head x2 plus gamma 3 head x3. Okay, so you find out error term, so y minus y head. So obviously you here, the moment you will get e, then obviously of course the r square is high and f is statistically significant, gamma 0 is significant, gamma 1 significant, gamma 2 significant, gamma 3 are significant, means all these parameters are statistically significant at the higher level, and r square is very high and f is also highly significant at the higher level. So still you need to have the heteroscedasticity check. So to go for heteroscedasticity check, you have to go for again to fit another model, say e equal to alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus alpha 4 x1 squares, then plus alpha 5 x2 squares plus alpha 6 x3 squares plus alpha 7 x1 x2 plus alpha 8 x1 x3, okay, then plus alpha 9 x2 x3 plus u. Okay, u is another error term. So now you estimate this model and have the r square value. Okay, find r square. So now you multiplied n with r square, then it is followed by chi square with k minus 1 degrees of freedom. If this is statistically significant, then it is the presence of heteroscedasticity. If it is not significant, then there is no such problem of you can say heteroscedasticity. So you have to proceed with the means we can use that model for policy use and you can say forecasting. But if it is significant, then again you have to redesign, restructure till you get the better fitted model. Okay. Now another way you will get the model, there is a test called as a BPG test. Okay, there is a test called as a BPG test. What is the BPG test? BPG test is you first design a model like this: y equal to summation beta I xi I equal to 1 to n plus beta 0 plus ui. Okay, so now you have y head, you have e followed by y and x. Okay, followed by e. So y minus y head. Okay, so then once you have y minus y head, then obviously you find out error variance sigma squares. Okay, so now in the step 2 you would try to regress sigma square equal to alpha 0 plus summation alpha I xi I equal to 1 to n plus u. Okay, then you find out explain some squares. You find out explain some squares. Okay, so now explain some square divided by 2 followed by chi square k minus 1, chi square k minus 1. Okay, chi square k minus 1, and if it is significant, then there is a problem of heteroscedasticity. If it is not significant, then there is no such heteroscedasticity problem. So that means you can use that particular model for forecasting or policy use. So these are the detection criteria through which heteroscedasticity can be observed, or it can give you the indication message that whether there is a presence of heteroscedasticity in the system or in that particular problem or not. If there is such problem, then obviously you have to find out its alternative, or you can say restructure, redesign, then till you get the model best fitted which is free from heteroscedasticity. But sometimes you will face lots of difficulty. So, to solve a particular problem, there is the introduction of another problem. For instance, if you solve heteroscedasticity problem which is already cured through autocorrelation problem, let us start with some estimated models which is no autocorrelation. But when you will go for heteroscedasticity, you can find that there is some problem of heteroscedasticity. So, you have to redesign restructure. So, in that case you will find that redesign restructure will give you the give you the heteroscedasticity free problem in solution. So, the moment you solve that heteroscedasticity, then in that particular case redesigned models may be extra problem, create extra problem, like it can have again autocorrelation problem. Again you have to try to solve the autocorrelation. If you are success, then it's very okay. If it is not success, then you have to find out some compromise rules. So, how close autocorrelation you have in the model and how close heteroscedasticity you have in the model. It's because presence of autocorrelation is not a serious issue. It may be because it is allowed 1.5 to say 2.5, but presence of heteroscedasticity should not be allowed. It should be removed. It is because the variation of data points will be very much negative factor for the econometric modeling. That in that case it cannot be considered as the best model. So, that's why you first solve the heteroscedasticity problem and you will come to other problems so that it can be solved accordingly. Okay. So, this is how the structure of heteroscedasticity problem. So, that means we get to know what is the various means the definition of heteroscedasticity, nature of heteroscedasticity, causes of heteroscedasticity, then its detection criteria. Now, we like to know what are its solution criteria. Obviously, before going to solution, the obvious question is whether it is a problem for econometric modeling. In fact, most of the times we have already highlighted it is obviously it is a problem. So, problem means since it is not a it is having a blue concept, means that it is not going in favor of blue theorem. So, best linear unbiased estimator. So, obviously it is by default it is a problem, and that model cannot be used for forecasting or policy use, and we cannot say that this model is considered as the best model. So, that is why means it is a serious problem, because it is not fulfilling the properties of blue theorem. So, it needs solution. So, you need to find out some solution for this curing the heteroscedasticity. So, what are the solution you can find out? That means solutions. Okay. So, the solutions are basically divided into two parts. One with the assumption about sigma square I, and general solutions. Why assumption about sigma square? Because it is the covariance of u upon I ui uj equal to sigma square I for I equal to j. Okay, I equal to j. What it means? It is not equal variance. So, sigma square I means sigma square I may be some functional form. Let us say it is sigma square by x. Okay. So, let us say this is in that particular format, or you can say this type of case sigma square xi, this is the form. So, that means what you have to do? So, you bring a transformation rule. Let us say you have a model y equal to alpha plus beta x I plus e. So, what you have to do, since it is coming like this way, so you better otherwise you take like this sigma square xi say. Okay, that will be better indication. So, now what you have to do? So, you divide xi both the root xi both the sides. Okay, you divide root x both the sides. Okay, so then you will get a particular solution by the root. This is one variable and this is another variable. So, now you again go for estimations. The error then once you get the estimations, and if you go by heteroscedasticity check, then obviously the problem can be solved. So, that means here this particular structure is called as a otherwise you can apply this weightage least square method. So, you apply some weight which can minimize this unequal variance. So, giving weightage to that particular variables will you will solve the heteroscedasticity problem. Okay. Similarly, best idea is here regarding say assumption about sigma square I means you see what is the form of sigma square. It may be sigma square I equal to say alpha plus beta xi, another format. So, you divide alpha plus beta xi with y and x, then you again re-estimate the means transport variable. Obviously, you will get a situation where there may not be any heteroscedasticity problem. So, that means there is a need of proper transformation with respect to sigma square I. Okay. So, you first know what is the sigma square I, then with respect to sigma square I you will go for this weightage factor or transformation rule. So, this is one way to solve this particular heteroscedasticity problem. The second aspect of heteroscedasticity problem is means we categorically divided in the other part is called as a general solution. So, general solutions means you can go for transformation rule also, general transformation rule. For instance, obviously you can start with very in inspection method. If you find there is some kind of variability, means a huge variability, there may be some presence of outliers, etc. So, it is better you start with the transformations. So, if you start with the transformation, then obviously at the end you may not have a heteroscedasticity problem. But if you by inspection, if you are getting some kind of variation and you are not transforming and going with original setup, then obviously you will again go back to the original position, because this estimated model end of the estimated models you may not get the heteroscedasticity solution. So, it is better if you by inspection, if you will get first before you handling this particular problem, by inspection you observe whether there is such type of heteroscedasticity problem may be there or not, then you go for transformation. But any problem can be start with a transformation, but you can do that, but that is not good choice always, because if you apply the transformation rule very beginning, then you are going to lose the originality of that particular variable. So, that is why it is better you should not start with the transformation if it is not necessary or not required. Then you find if it is necessary, then you have to go by transformation. It is actually just like a circle, you have to move one after another structure till you get the best fitted model. In one stroke, it is very difficult to find a solution which can be considered as the best for best fit models which can be considered as a policy use or forecasting. So, it is very difficult to get in the first end. So, you have to go step by step till you get the best fitted models. Okay, this is how the another solution to the general transformation. Either it is called as a general transformation rule, this is called as a general transformation rule, or transformation with respect as per the structure of sigma square I. So, because sigma square if it is not equal, then obviously sigma square I having some functional form. So, that functional form has to be observed very carefully. Then you have to apply or multiply or subtract, divide, whatever you like, till you get the models which is free from heteroscedasticity. Okay, this is another solution for this particular problem. Second solution is in fact in this transformation rules there is a lots of transformation criteria. You can go for log transformation, you can go for exponential transformation, you can go for some methodological transformations, you can go for some different transformations. So, every transformation rule structure is completely different, and like different techniques will give you different types of results, and sometimes some technique will give very positive for your objective, and some transformation will give you for negative for the particular objective. Similarly, in that case also in the transformation rule like technique, transformation rule also give you something positive for you, something for negative for you. So, that is why what is my suggestion is that you go transferring the variable one after another structure. If in one transformation rule you will get it, then obviously it is good for you, you are lucky enough. But if not, then you have to sequentially go with a different transformation till you get the best model which is free from heteroscedasticity and other problems. Okay, so transformation rule cannot be unique. It is in fact by definition it is very multidimensional in nature. So, there are many ways you can transfer the variables in different format, different structure, and that can be, that is essential, and that is needed, that is also required to do to get the best fitted model. Because if model itself means econometric modeling is a decision making science if it is defined in proper way in a broad angle. So, that means there are various alternatives must be with you. So, within the various alternatives you have to find out the best possible solution which can be considered as the policy use or which can be considered for forecasting issue. So, that is how you must be very careful about the transformation rule. So, we have a separate lectures for digit test. During the digit test I will discuss detail about the transformation rule. If possible we will highlight all these issue details there. Okay, this is another means it's about the transformation rule. Then sometimes redesign the variables. Okay, variables may be for instance you are using the term exports with the impact of exports on inflations. Okay, so so you are starting with the direct amount of exports with the inflations, and by that way you will get heteroscedasticity problem. So, in the next step what you will do, you transfer the export into a percentage of amount of export as a percentage of GDP. This is another way to transformation rule. So, if you instead of using direct exports, if you use export as a percentage of GDP, then obviously that transformation may solve the heteroscedasticity problem. So, you must be very careful, because the way you will transfer this like this is require lots of theoretical knowledge. Export as a percentage of GDP is a meaningful interpretation. So, that is why it can be used, but if there is no such meaningful interpretation, you cannot use for the you cannot transfer that variable arbitrarily. So, there should be logic behind it, there should be proper theory behind this, then you will go for that type of transformation. Okay. So, then similarly there is another tricks called redesigning the mathematical form of the model. Since mathematical formulation of model imperfection of the model will give heteroscedasticity problem, so you continuously redesign the model, because in the first hand you cannot observe whether this particular functional form is having heteroscedasticity, free from heteroscedasticity or not. So, ultimately once you have, then again you have to redesign the mathematical formulation of the model, then again you test for heteroscedasticity, it may be a solution for the heteroscedasticity problem. Okay. So, this is another way to solve the heteroscedasticity problem. So, then another way you can solve the heteroscedasticity problem is improving the data collection technique. Okay. So, because I have mentioned there may be a respondent, some are very positive to your questionnaire, some are very negative to your questionnaire. So, this side it is unbiased and this side is biased, and if you club together, then obviously there will be heteroscedasticity problem. So, so you should be very good respondents, and that should be the respondents must be homogeneous in nature. They can understand your problem in equal level or equal angles. Obviously, the sample points cannot be very or cannot far from the other sample points. So, as a result, heteroscedasticity problem can be solved. So, that means what is that suggestion is that improving data technique will also solve the problem of heteroscedasticity. So, by like this, there are several other rules also through which heteroscedasticity problem can be solved. So, so we have discussed what is the exact problem of heteroscedasticity in nature, then its consequences, causes, and detection criteria, and the solution criteria. And obviously, we have in between we have also discussed whether it is a problem. Obviously, it is a problem. You need to have a solution, and for that solution, you must have your approach must be positive. You must have a huge knowledge on technique wise, transformation information, etc., so that it can be give you lots of positive things how to solve this heteroscedasticity problem. With this, we will close this chapter. Thank you very much. Have a nice day.